The question? Oh, let's see if it's balanced. So 3 iron. 3 irons. I'm balanced by iron, so this gives me 3 sulfates, 6 sodiums, 2 phosphates, 2 phosphates. So it is balanced. And the state were aqueous, and solid. That's correct. Aqueous, we'll just leave off. Do you have a question?
How come you put the sodium first instead of the iron?
It doesn't matter. Myself, I would have put the iron first. Because I would have went iron, phosphate plus sodium sulfate. And so, but it really doesn't matter what order they're in. Yeah, but you're right. I would have put the sodium compound last. But lots of people will do, okay, they form sodium sulfate and then iron phosphate. Which iron is it? There's iron 2 and iron 3, so we have to pay attention to that. Okay, this would be the CE. What's the driving force for this? Precipitation. And so normally you just mark it like this. DF, PPT. Like that. That would be the driving force.
Do you want us to do that?
Yeah, you're going to have to do that also. You have to tell me what the driving force is. All right, this is what we're going to call the CE. And then after the CE, we have the IE. And so what do we do with the IE here? Yes. Split them up. And so this splits up into what?
3 Fe2 plus.
3 Fe2 plus.
And 3 SO4.
Yeah, 3 SO4 2 minus. It has to balance. So this balances here. Okay, and then 6 Na. Don't forget the charges. Plus
2 PO4 and that's 6 Na
6 Na plus
and 3
SO4 2 minus. And then plus Fe3PO4.
yeah, Fe3PO4 2 solid. Oh, good. Okay, and then the NIE for this?
so 3 Fe2
Plus
2
2PO4 2 minus.
There's also
Fe3PO4 2.
Okay, so that would be it. So this is just your typical precipitation reaction, double replacement. There's the 3 driving forces for this is precipitation and what else? Other driving forces? Gas formation. Gas formation, the most common one is what? When you form what compound? Yeah, carbon dioxide and water. That forms when you make hydrogen carbonate or carbonic acid. And so that's the most common one. That one you should know for sure. If you form carbonic acid, it's got to decompose right away in the CE to water and CO2.
So why did you make? I would have left it as 2Na3 plus. Why'd you turn it into 6?
2Na3
plus.
3 plus like this?
3 on the bottom.
Or 3 on the bottom?
3 on the bottom plus.
Yeah. Because it doesn't form triatomic species. When we look at the lattice of sodium phosphate, the sodiums aren't linked together. There's something wrong there.
It would also signify that each sodium is like 1/3 of right?
Yeah. That would also signify that each sodium is 1/3 positive. Exactly. So that would be weird. This gives it Na3, not Na3, Fe3. That's what I wanted. Fe3 is Fe3 PO42.
Yeah.
Oh, actually, I'm sorry, we're not looking at this. This is how the Fe3PO4 lattice is. Your question is about Na3PO4?
No, like when you split it up into the ionic equation. Because now I'm just concerned that I've been doing it incorrectly on all the other equations, because if you're splitting up S6 and a plus, just wanted to make sure that mine was correct or incorrect. Because they're going to cancel out regardless, 2Na3.
Right, but you need two phosphates, so you have to have enough of the lattice to do that. And the sodiums are going to be packed in there, although it's hard to see in all these where the sodium goes. Maybe this one is okay. There's some superposition here, so it might be a little bit hard to see, but the sodiums aren't actually linked together. So you wouldn't have this. This would be a triatomic ion. And when somebody sees this, they're thinking you have 3 sodium atoms bonded together, and then this whole thing carries a +1 charge. Is that what you're trying to? And then we have 2 of these. So if you wrote it like this, then that would be 2 Na3, each one having positive charge. Is that what you're intending to write? Whenever we have an ionic lattice, all the ions break apart completely. And so all the sodiums are going to break apart from the phosphates here. Although this doesn't show the whole ionic lattice, this shows a part of the ionic lattice. A part of the ionic lattice is like this. These sodiums become completely separated from the phosphate. Here. Completely separated. And so you can think of the same thing. The only one that does this is mercury. Mercury is a weird one because it forms a diatomic cation, Hg2, 2+. But none of the other ions do this, when we're looking at monatomic, like iron 3 or Na. It doesn't stay together. Those sodiums are actually not bonded together. Those sodiums are actually in the lattice separately. Does that make sense? Or not really? We can talk about it more later.
I just gotta check my other problems.
Yeah, check your other problems because, you don't want to do that. Okay. All right, so make sure you can repeat the reactions we did in class, and then what you want to do for the lab, yesterday's lab, is start doing all the equations. And so we did sodium. What did we do with the first reaction? And so we had a series of double replacement reactions and a series of single replacement reactions. So what you were going to do for each of the reactions in lab is write out the equations. You write out the CE for the double replacements, you write out the CE for the single replacements, and then you determine the driving force. Not all the reactions had a driving force, but you should be able to tell, predict that. And then if there was a driving force, you're going to write the IE and the NIE in addition to that for those. So this would be good practice for the test. So why don't you work on that over the weekend as a practice problem for the test?
No, like which 3?
Yeah, the CE, the IE, and the NIE, and the driving force.
Good practice problem.
Yeah. Do those for the test.
Right.
Okay, any questions on this? We're going to leave this and then we're going to go back to chapter 10. So the next section in chapter 10 is something called percentage yield. And so when you pop popcorn, do you get 100% yield of popcorn? No, you get less than 100% yield because you're left over with some unpopped kernels. And so what percentage yield is this? Well, it varies. Sometimes you get more, sometimes you get less, depending on how many unpopped kernels there are. But typically, what we want is a higher percentage yield. A higher percentage yield is better. And so in this case, they started with 20, and they ended up with 16 pop and 4 unpop. And so what yield is that? Well, that's 16 out of a theoretical of 20
Right.
gives us 80% yield. Does that make sense? The same thing happens in chemistry. When you set out to make something, maybe not all of it reacts, or maybe you lose some. Let's say, some of the popcorn fell on the floor, you lost some. That would decrease your yield too. Well, in chemical reactions, that kind of stuff happens a lot, or things don't happen so cleanly. And so how do we figure this out in terms of a chemical reaction? So here's this is one of the ones you did yesterday. You took some sodium sulfate solution and mixed it with some barium chloride, and you got a precipitate of barium sulfate, which is this cloudy white PBT, and you're left over with sodium chloride. Sodium chloride is just going to be the CCS here. And then what we can do is we can separate out the barium sulfate by filtration, dry it, and then weigh it. And so in this case, they weighed out 16.75 grams. Now, what we want to know is, in theory, how much? Was that 100% yield or less than 100% yield? Maybe not everything reacted, or maybe we lost a little bit. And so we'd like to know what the percentage yield is. In order to figure out the percentage yield, we have to figure out something called the theoretical yield first. In theory, how much should have formed when we did that? And so theoretical yield is determined by stoichiometry. And so let's look at some percent yield problems here. This particular problem. Okay. Yeah. Slightly different problem. Let me just think up the problem here first. All right, so normally when we do these reactions, there are two ways that a chemical reaction is done. So if we're going to mix some iron 2 sulfate and some sodium phosphate, the two ways we could do it is, one, stoichiometrically. If we do this stoichiometrically, stoichiometric means we have just the right amounts. And that's typically done in something called a titration style reaction. A stoichiometric reaction. An example of this would be titration. We'll talk about titrations later on. But this is just the right amounts. And so I have just the right amount of sodium phosphate to react with iron 2 sulfate. But we don't often do things by titration. The other way we do it is by what we call limiting and excess reagents. So let's say our goal in this particular reaction is to get all the iron out. If we want to get all the iron out as a precipitate here, or we want to get all the phosphate out, as a precipitate here, that would involve two different strategies. So for example, if I want all the iron out of this, then what I'm going to do is I'm going to have a limiting amount of this and an excess amount of this. So I'm going to add more than I need. That will ensure that I get all the iron out as precipitate. Versus if I wanted to precipitate out all the phosphate, then typically what I do is I'd have a limiting amount of this and an excess amount of this. And that would ensure all the phosphate gets precipitated. Otherwise, I'd have to carefully control the experiment to get just the right amount of these two to react completely. And so let's say I want to get rid of all the iron. And this is a solution here, aqueous. And so let's say I have 10.5 grams of FeSO4 solid that I use to make this solution. And so all together, there's 10.5 grams of FeSO4 in the solution. And then I'm going to have excess. Excess is just abbreviated excess. Sodium phosphate. And so what I'm going to do is I'm going to use stoichiometry to predict how much of the precipitate I should form. And so this is going to yield how many grams of iron 3 phosphate. Okay, so let's go ahead and try this. This is going to be a stoichiometry problem. That's mass of A to what? We're going to go from mass of A to moles of A, which will be FeSO4, moles of A to moles of B, which is going to be Fe3PO42, and then moles of B to grams of B. And so why don't you try that? This is your standard stoichiometry problem that we do. In this case, we're going to say we have plenty of this. So we don't worry about that. We're just worrying about this one here. And so we need some molar masses. So iron, and you're going to be given a periodic table. It's 55.85 is the mass. 55.85. The units for mass are either U per atom or grams per mole of atoms. It's the same number. And so usually you leave the units on and then act on it again. Sulfur, 32.07 according to this, 32.06 according to your periodic table. And so we'll just go with this periodic table here, or actually we'll go with yours, 32.06. Oxygen is 16.00. We leave these to 2 decimal places, so this is why I round these. Sodium is 22.9. Sodium is 22.989. So we'll just go with 22.99. Next. What else do we need? Phosphorus. Phosphorus is 30.97. 30.97. So normally, like a periodic table like that has more digits. You know, it's more precise, more accurate. But usually when we calculate molar masses, we don't need that many digits. I mean, we could easily have 4 sig figs by going 2 decimal places. And so, normally, if I'm given a periodic table like this, I'll just go ahead and round all masses to 2 decimal places. That way, I'm not punching so many keys in the calculator all the time. And a lot of those digits I'll round off anyway. Okay, so I forgot to record this, but unfortunately my battery is not going to last. I forgot my charger. So I hope this made sense, you know, the typical yield. And so what did you get for the theoretical yield? What is it?
2.68 grams.
2.68 grams of ammonia is our theoretical yield. But, typically in this reaction, we lose a little bit, 7.2%. And so that's not how much we expect to have at the end. How much do we expect to have? And so the next conversion factor is, if this is the theoretical yield, then I'm going to say I'm going to have 100 grams of ammonia theoretical yield over 92.8 grams of ammonia actual yield. And so the actual yield is going to be a little less. And so what does it come out to? $2.487 grams, which comes out to 2.49 grams of actual yield for the ammonia. Is that what you guys got?
Yeah.
So this is like if I planned to bake 100 cookies and I ate 5 of them, that would be here. It would be 95 out of 100 cookies you have actually. Okay, there's one other type of problem, and that is if I have a target amount that I want. And so there are only 3 types of problems here.
This is going to be on the test?
No, this is not going to be on the test.
Can we go over one last thing for them?
Yeah. What is that?
It's the bonus question.
Here. This one?
Yeah.
For the ion compounds, we have this.
I was peeling these things.
Well, actually, before we do that, can I just say the last type of problem for this? The last type of problem that we're going to see in this particular section is this.
Searching.
The last type of problem we want is here. We have a target. So would be like 35. 35 says, okay, we want this.
You have a touch. No.
No, it's not a touch screen. I don't know what's wrong with it.
It's
It's a brand new computer, but has anybody else experienced this?
Yeah.
Only with my
In the other classes too? All these are defective somehow. There's some kind of problem with it. I don't know.
You know what you could do if you really wanted to, you could pull up the snipping tool and just take a screenshot.
Oh, yeah. That's true. Then it wouldn't,
It'd be kind of annoying to keep having to do that.
yeah. Right. The other type of problem is this. Let's say we want, this is 500. So this would be like 500 cookies. If we want to make 500 cookies and the yield is 88.8%, then how much do we have to, how much hydrogen do we have to have? So what we're going to do is we're going to have excess nitrogen, limiting reagent of hydrogen. So let's take a look at this problem here, 35. Why don't you try this one, number 35, and see what you get.